All right. Well, then in that case, I think it's time to start. So, good morning, everybody. Um, let's see, starting out with a little bit of today in internet history, as usual. 22 years ago, the Netflix website was launched. At the time, they had a whole 925 movies, which you could order on their website. And they emailed you, or rather, they mailed you the movie on DVD. They didn't actually start streaming for another 9 years. Um, a year after launching their website, they tried to get Blockbuster to buy them, which didn't happen. Um, I imagine a number of people have kicked themselves over that. Last year Netflix netted, coming up on $2 billion. Blockbuster, meanwhile, has one remaining store in Bend, Oregon, or at least they did as of a few months ago. I hope they're doing okay under present circumstances, but don't actually know. Um, but so moving on, lecture. Um, Today we're primarily going to be trying to put some pieces together to give sort of a holistic view of how a bunch of stuff works together. And to get there, we're going to answer some sort of lurking questions. So in the past, we've talked a bunch about L3 and specifically about IP. And we've talked about, common routing approaches, both at the intradomain and interdomain levels. We've talked about IP addresses, their structure and their properties with aggregation and so on. And we've talked some about L2, mostly with a bias towards Ethernet. And, again, we talked about some routing approaches that are used. Link state is used in L2 routing sometimes. And we talked about learning switches and spanning tree protocol, which are very common in Ethernet traditionally and are a bit of a different beast. Not even always classified as routing, but we classify them as routing. On the other hand, I don't think we talked about Ethernet addresses at all. So today we're going to fix that. And we're going to fill in some other gaps, So again, we're going to have this sort of bias towards Ethernet and IPv4. There are generally, similarities with other L2s and L3s, like, Wi-Fi as an L2 is similar in a lot of ways to Ethernet, and IPv6 in a lot of ways is similar to IPv4. On Ethernet, we're going to talk about addresses. We're going to talk about the history of Ethernet. And then going to kind of bring it around and talk about modern Ethernet. And then we're going to talk about how L2 and L3 really fit together. For example, we know that there's routing at L2 and at L3, and some of you may be wondering, when we do one and when we do the other, and hopefully we're going to clarify that today. We'll also talk about two protocols mostly relating to addresses, which are ARP and DHCP. And then we'll do an example where we see a whole lot of pieces, both old and new, sort of working together. If there's time, we'll finish up with a discussion of network address translation, but we're definitely not going to have time. So let's talk about Ethernet. Start with why so much focus on Ethernet in this class? And the answer to that is just because it's huge. It's used all over the place. It's a super common L2 technology. It's been around for a long time, and it's still totally relevant today. But before we get into it, let's talk about this guy, Norman Abramson. And so in 1968, he'd recently left California and become a professor at the University of Hawaii. Before that, he'd been at Stanford, and I'm not sure if he was part of the Berkeley faculty, but I think he at least taught some classes at Berkeley. But at one point, he went on a trip to Japan, and on the way, he stopped over in Hawaii for a couple days. And while he was there, he got the bug for surfing. And so shortly thereafter, he got a position at the University of Hawaii, which is on Oahu. And so at the University of Hawaii on Oahu, they had a computer, a IBM 360 mainframe, a famous computer. And they wanted to allow access to it from people around Hawaii on other islands. I think mostly on Maui and around Oahu, but maybe some of the other islands too. And his solution was to build this thing called AlohaNet, which is a really torturous acronym for Additive Links Online Hawaii Area. And while the system was like definitely tuned to the specific problem they were facing, its design has been hugely and perseveringly influential. It's still really relevant today. The kind of Aloha techniques are used in many, many current wireless devices. And so we'll come back to Aloha in a second, but first I want to talk about this idea of shared media. So in a radio network, all the nodes are utilizing a shared medium, that medium being the electromagnetic spectrum in some area. And because the medium is shared, transmissions from different nodes may interfere or collide with each other. And when that happens, it's going to garble the communication. It's like if two people are talking at once, it becomes hard to make out what anyone is saying, right? So we need a system for allocating the medium to everyone that wants to use it. And we can call that system a multiple access protocol. So there are lots of ways a multiple access protocol can work. I'm certainly not going to give an exhaustive list, but I'll list some of them. And so one way is that you can divide up the medium by frequency, like so every node gets its own frequency to transmit on. And sometimes this may be a great solution. In many situations, it's not. If your traffic is bursty, for example, then like a lot of your frequencies may be idle a lot of the time. And since there's only so much like useful electromagnetic spectrum to go around, this is sort of unfortunately wasteful. Another way is to divide it up by time. And there are several ways of doing this. For example, one is to divide time into fixed sized slots, and each sender gets their own slot. And I think this is similar to a system we talked about in lecture 2, all the way back, for doing reservations. But ultimately, this has similar drawbacks to the previous approach. Like both of them sort of work on this idea of like a fixed partitioning of the medium. So a different approach are turn-taking approaches. And so like one turn-taking approach is a polling protocol, where there's some kind of coordinator that decides who gets to transmit at a particular time. And this is sort of like Congress or something, where, you have a chair who's like, the chair recognizes the senator from California and, gives them a chance to speak, and, they may speak. And then when they're done, the coordinator will ask someone else, and then that someone else will have an opportunity to say something. And so like Bluetooth, I think, for example, basically works this way. Another turn-taking approach is token passing. And so in this approach, there is like a virtual token, which is passed around. And only the one that's holding it can speak or transmit. And so this is similar to like the talking stick approach used famously by some of the people native to the Northwest of North America. And it's also used by a local network technology, a one-time competitor of Ethernet called IBM Token Ring. It's also used by a protocol called FDDI, which is used with fiber optic networks. So you can divide up the medium by taking turns through polling or token passing, for example. There's also random access methods. And this is what was pioneered by Aloha and is used in everything else that we'll talk about today. So getting back to Aloha, Aloha had a big node on Oahu. This is where the big transmitter was. It's where the computer actually was. And we'll call it the hub. It actually had a clever Hawaiian name. And then there were remote nodes spread across Hawaii. Like I said, I think most of them were on Oahu and Maui. I think at the peak, I think maybe there was something like 40. And Aloha used 2 different frequencies. So only the hub transmitted on one of the frequencies. And all of the remotes receive this, but since there was only one transmitter, there's no chance of collisions. And all of the remotes transmitted on the other frequency. So these transmissions could collide. And to deal with the collisions, they used a random access scheme. I'm about to explain how the random access scheme works, but is everyone clear on the context here? Anybody like me to repeat any of this? All right, so moving on. So I'm going to describe the pure Aloha random access scheme. There's a notable variation called slotted Aloha, but I'm not going to talk about it, but it's pretty similar. And so the idea here is pretty simple. If one of those remotes has a packet, it just sends it whenever. There's no coordination between the remote sites. And when the hub successfully receives a packet, it sends an acknowledgement. And if two sites happen to transmit at the same time, then there's going to be a collision, and the hub will have gotten garbled packets, and so it won't send that acknowledgement. And so if a remote doesn't get the expected acknowledgement, then it's going to wait a randomized amount of time, and then it's going to retransmit. The fact that the time is randomized is super important. Like, if all the nodes waited the same amount of time, then they just collide again. But by varying the amount of time, then the chance of a collision on a retransmission is lessened. And so that's it. It's super simple, but it's also kind of ingenious. I mean, this is not how people thought about doing radio transmissions before this point. So it was kind of a breakthrough conceptually. Anybody, any questions on the Aloha protocol so far? All right. So maybe you're thinking that this all sounds great, but aren't we supposed to be talking about Ethernet, which of course is wired and not wireless? And yes, you're right, but we actually already are. But before I really start, tying it into Ethernet, I do want to share a tale about AlohaNet because it's just too good. So AlohaNet was connected to the ARPANET, the precursor of the internet, way back, very early on in like 1972 or 1973. And a story that's told about this is that it's because Norm Abramson was at a meeting with ARPANET's program manager, Larry Roberts, and Larry stepped out of the room, and Norm just added AlohaNet to a list of sites that were planned to be added to the ARPANET. Just wrote AlohaNet on there, supposedly as a joke. But a few months later, they sent him the ARPANET hardware. So, according to the tale, he didn't even immediately remember why the ARPANET hardware showed up at the University of Hawaii. So, whether this was a historical accident or a cunning strategy or whatever, I don't really know, but it puts like AlohaNet way back into internet history. So anyway, back to Ethernet. This guy is Bob Metcalfe, the father of Ethernet. And it's not a great photo of him, but it's the best one I could find with a Creative Commons license. And in the full photo, check out who he's hanging out with. It's our friend, inventor of the web, Sir Tim Berners-Lee. I'm not sure if I mentioned it before, but Tim Berners-Lee has been knighted. So anyway, Bob Metcalfe, among other things, is known for Metcalfe's law, which basically says that like the value or impact of a network grows quadratically with the number of nodes because the number of possible connections grows quadratically, or actually triangularly, but whatever, close enough. And this rationale has been used to explain the sort of like booming growth of the internet, like it has more value, like quadratically as you add things to it. I think this is also used, really heavily when trying to get venture capital money for internet startups in the 90s. But in 1972, he worked for Xerox, which was doing really groundbreaking, influential work at the time, including designing a computer called the Alto, which was really the first attempt at a personal computer or a computing workstation. And the Alto did not go on to be a huge success as a product. And really, I mean, they tried to commercialize it with a successor called the Xerox Star, which they sold some of, but not that many. So as a product, it wasn't very successful, but as a sort of a, just a piece of work, it was hugely successful. It was hugely inspiring to all the personal computing that came after it. Apple in particular was super directly influenced by it. The Mac user interface was basically borrowed from the Alto. That's like the Mac was sort of like the first GUI interface that a lot of people saw, and it was borrowed from the Alto. I think Apple gave Xerox some stock to basically let them steal the interface. And so Xerox was talking about having businesses with like tens or maybe hundreds of these computers in one building, that was like a completely new idea. And they wanted a way to connect all of them. And they also wanted a way to connect these computers to another product that Xerox was working on at the time, which was the first laser printer. And so they needed to have this network that was going to be, pretty cheap, but it also needed to be, pretty good. It needed to be like pretty fast in order to like ship around like a bunch of high resolution images for their fancy laser printer, which could print pretty fast. So Robert Metcalfe was put in charge of developing this network for the Alto, and he had done part of his PhD thesis on AlohaNet, and so he thought, rather than run a separate cable to each computer the way that like every other early network worked, what if he just ran a single two-conductor cable and all the computers just connected to that one cable? So like Aloha, he was going to use this one cable as a shared medium. So early ARPANET and other things we've looked at so far this semester looked something like this. And Bob Metcalfe's Ethernet looked like this. And you can see how that might be quite a bit cheaper. So Ethernet sort of refined the Aloha scheme, giving us something called CSMA, or Carrier Sense Multiple Access. And the idea here is that Aloha was kind of rude. Like nodes just like send data and figure out if it collided later. And CSMA is sort of more polite. It listens first and only starts talking when it's quiet. And by listening, I mean that the network interfaces are sensing the signal or carrier from other nodes on the wire, hence the name. And so, you probably use a protocol much more like CSMA yourself when you're actually talking to people in real life, right? You kind of wait until there's a lull in the conversation, then you say your part. Hopefully you don't interrupt too much. But so like, this is a nice improvement, but it doesn't completely avoid collisions. It avoids a lot of them, but not all of them. So let me ask you, why not? Why doesn't this avoid collisions completely? And again, you might consider whether this same basic scheme completely stops collisions in your real life conversations with people. So anyone have an idea? No? Okay, here's a couple answers. Yeah, so when like multiple people think it's quiet and they both try to talk at the same time. Right, yeah. So I think you're onto something here. And so I'm going to phrase it as the key problem here is propagation delay. And so let's take a look at this using this time-space graph. And so time moves down the graph, and the horizontal axis is space. And so we've got 4 nodes, 4 hosts on this network, H1, H2, H3, H4, and they're separated from each other by some space, like as if these were 4 computers connected to a single Ethernet cable at some distance from each other, right? And so at time 0, H2 is going to start to transmit a packet. And as time goes by, the signal is going to propagate outwards, right? Taking time to spread out in space to reach the other nodes. If you were a physicist, I think you'd call this the light cone. And okay, quick side note or a quick quiz. What is this time that I'm showing here with the bar? We have a name for this. This time right here. What is that? We talked about several kinds of delay earlier in the semester. What is that one? Right, it's the time that H2 is transmitting, or the transmission delay, right? That's what that is. Good answer. So, this is, from the top of that to the bottom of that, from the kind of peak to the peak. That's the time when H2 is transmitting. Okay, so back to this graph. Let's look at time 2. So at time 2, H3 has heard H2's packet. It knows that H2 is transmitting. So if it has a packet to send, it's not going to send it now because it would collide, right? That's the carrier sense. But if we look at H4, H4 has no idea that H2 is transmitting, right? It's happening, but it doesn't know it yet. So H4 might start sending a packet of its own right then. And as that packet propagates, it's going to collide, right? So all this like deep purple area here, there's 2 packets on the wire. And so, these packets are going to be ruined for everybody. And so the solution here is to add this additional mechanism, resulting in what's called CSMA CD. And so the CD here is collision detection. And basically it just means that you also listen while you talk. If you hear someone else at the same time, you shut up. Don't even bother sending the rest of the packet because it's already been ruined. And there's a bit more to it, but that's the basic idea. So does this make sense to everybody so far? Anybody want to do a hand raise or anything? This is kind of making sense. All right, I'll take it. So a final word on retransmission. We've already talked about how you wait a random amount of time before retransmitting. But if there's a lot of contention, a lot of nodes waiting to transmit, then you may still keep colliding. And so a solution to this is to use randomized binary exponential backoff. And all that's really saying is that if a transmission, if a retransmission also collides, then you wait up to twice as long before trying again. Again, you wait a random amount of time, but up to twice as long. And basically you continue doubling for every subsequent like re-collision. And so ultimately this transmits quickly when it's possible, but it slows down when necessary. And you may remember you actually already have seen a binary exponential backoff before. Back in discussion 8, the TCP retransmission timer keeps doubling. And so that wasn't a randomized version, but this notion of sort of like binary exponential backoff is pretty common in network protocols. So to sort of sum up where we are so far, this Ethernet, which I'll call classic Ethernet, using a shared medium and like a single coaxial cable in the case of the original Xerox Ethernet, used a thick, generally yellow coaxial cable, often called Big Yellow. And it used a random medium access protocol, CSMA CD, which was inspired by Aloha. And so the kind of key ideas here are carrier sense, don't interrupt if someone else is transmitting. Collision detection, which is, notice if another node starts transmitting at the same time. Randomness in when you start to retransmit so that you don't collide again. And exponential backoff, where the higher the contention is, the more conservative you become. And I didn't put it here, but like key to all of this is that Norman Abramson liked to surf and moved to Hawaii and invented Aloha. So everybody good on this so far? Anybody questions? All right. So let's get into Ethernet addresses and service types. So on this shared medium, like if you transmit, everyone hears it, right? If H1 puts a packet on the wire here, then H2, H3, H4, H5, they're all going to get the packet. Like the signal is going to show up at all of them. So the L2 address isn't really useful as a locator, but it is useful as an identifier. So what am I talking about? Like we've used this postal metaphor for networks in this class before, right? But like here, there's no need for an address to help you find the right street or anything like that. It's sort of like everybody's already in the same dark room and you talk and everybody will just hear you, right? But you still want to say their name when you're talking, like the name of the person that you want to talk to, so that everybody knows whether you're talking to them or not. So like, in contrast to IP, there's no real like routing here. There's no aggregation. These addresses are like simple flat addresses. And again, I'd say they're really less like an address and more like a name in some ways. And so the actual format of these addresses is that they're 48 bits or 6 bytes. They're usually shown as 6 two-digit hex numbers separated by colons or dashes. And the addresses are typically stored permanently in the network interface hardware itself. So sometimes they're called burned-in addresses, which has to do with the term that used to have for programmable ROM chips, which is called burning a ROM. And they can often temporarily be overridden by software while the system is running. And in some cases, you can change them more permanently, like by updating a piece of flash memory. On old hardware, like I said, they were often stored in like a separate programmable ROM chip. So you could just like pull that chip out and put a different ROM chip in to change the address. But like they're relatively difficult to change. Because of that, you'll often find them like actually printed on devices. So taking a slightly simplified look at the structure of these addresses, there are 2 bits which are sort of like flags, and we'll talk about one of them in a minute. And then there's 22 bits which identify like a company or an organization. So usually this is like the manufacturer that made the device. And then there's 24 bits to identify the device itself, like a serial number basically. And so like here's a USB Ethernet adapter. And on the other side, there's a 12-digit hex number. And those are its Ethernet address. They didn't put the colons in here. Often they've also got a barcode form of it too. Businesses use these like to track the devices on their network. Like they'll have issued this adapter to some person and they will have like swiped the barcode to enter it into a database just because it's easier to type in. And that way, when they see traffic on their network from this Ethernet address, that they'll know it's some user. Anyway, you can look up the first 3 bytes here, 0050B6. You can look those up in like a registry of device manufacturers and find out that this device was made by a company called Goodway Technologies. You can in fact go to their website and find this thing on it. So usually these addresses are supposed to be globally unique. So like each manufacturer has their own code, and then they should fill in the other 24 bits with some value that they don't use for any other device. We've got global uniqueness as a property for IP addresses also, but the reasoning here is kind of different. For IP, it's because all the addresses are really all supposed to be on the same network. But for Ethernet, that's not going to be the case, right? Like the L2 addresses, the addresses on one Ethernet network, like shouldn't ever touch the addresses on another Ethernet network. But since you can't easily change the addresses and you don't necessarily know when you manufacture them, like if 2 particular devices are going to be on the same network or not, the easiest thing to do is just make them all unique. Is this all clear so far? Ethernet addresses so far? All right, so a final note here, just sort of anecdotally, I've heard that like some manufacturers may reuse addresses. In particular, they may do it when selling devices to different markets, like if they sell devices to different countries that don't communicate much, don't cross over much, or if they sell like some consumer equipment and some equipment to like ISPs. So I've heard that this happens and that people usually get away with it, but it sometimes causes headaches when you end up with two devices on the same network with the same Ethernet address. If you think about it, they only have 24 bits for the device ID. So like that's up to 16 million IDs. And there are maybe a few 100 million servers on the planet. And of course, lots of other devices too, routers and switches and that sort of thing. And many servers have more than one network interface. And of course, over time, like old adapters might break or need to be replaced or upgraded with new ones that are faster and that sort of thing. So like maybe 16 million isn't really all that many. Um, and then there are virtual network interface devices. Like if you have a virtual machine, it probably has a virtual Ethernet adapter in it. And in my experience, the way this works for a lot of virtualization solutions is they just pick a random number essentially to be the Ethernet address. So there's no real guarantee of uniqueness there either. And so all of that is just to say that Ethernet addresses are mostly unique. All right, so moving on to service types. We've talked about a couple this semester so far. We've talked about unicast. That's sort of our default assumption, where you're sending to one specific recipient. And then we also talked about anycast in the context of DNS. On classic Ethernet, it's also trivial to support broadcast. And so broadcast is just sending to everyone. In the context of Ethernet, this means everyone on the same Ethernet network, like everyone on the same Ethernet cable. And this is so easy just because, the packet already reaches everybody on the cable, right? They just need to be listening for it. So this is implemented by using an address which is all ones, so 6 bytes of ones. FF, 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 FF is the Ethernet address for broadcast. And so again, this really only influences the receiver. Like all it has to do is listen to the broadcast address as well as its normal Ethernet address. The network itself behaves just exactly the same way. Note that like the internet does not support the notion of a universal broadcast. You can sort of imagine the problems we might have if it was easy to send a packet to literally everyone on the internet. But for Ethernet, it's easy. So Ethernet can do broadcast, and it can also support a service type called multicast, which is basically when you want to send to all the members of a particular group. And so you can sort of contrast this with anycast, which was sending to one member of a group. And much like broadcast, like this is really pretty trivial for Ethernet. Like a group is just a special address, and whether you're a member of the group or not is just a matter of whether you're listening to that address or not. So I mentioned those flags in the Ethernet address, and one of them basically marks whether an address is a multicast address or not. If it's a 1, then it's a multicast address. And so specifically, it's this bit right here, the lowest bit in the first byte of the address. So all normal Ethernet addresses are going to start with an even number because that bit's going to be 0 for a normal address. On first glance, this maybe seems like a weird bit to have chosen, but it's actually not. On the actual wire on Ethernet, the bits are sent from the low bit to the high bit, and from the first byte to the last byte. So this is actually the first bit that's of the address that's actually sent on the wire. So note that the broadcast address is all ones. So the multicast bit is set. So like the broadcast address is really just a special case of the multicast addresses. A quick example of when Ethernet multicast is used that maybe connects to your own life a little bit, like how does a Mac know when there are things around it to AirPlay to? Or how does your Mac know like when network printers are nearby that you can print to? And the answer is that they're communicating over the local network using multicast. maybe it's Wi-Fi and not Ethernet, but they're basically the same. And so your computer occasionally sends queries that basically say, I'm looking for a printer, or I'm looking for an AirPlay screen. And it sends them to this particular multicast address. And printers or TVs or whatever are listening on that address, and they send back responses. And just to kind of tie this back to stuff we've talked about already, it turns out that these queries and responses are actually all formatted as DNS records. So it's like a bunch of pointer and serve and text records. But unlike when we talked about DNS before, this isn't like a global, and there's no central, server infrastructure either. It's really just each device like is listening and responds when it sees a query that's relevant to it. And so this is called multicast DNS or MDNS, and DNS service discovery or DNS SD. Windows does something like really, really similar, but not identical for similar stuff, like, showing the local computers on a network. So anyway, an example of using multicast on a local network. And finally, I wanted to note that there is such a thing as IP multicast. For a brief period of time, there was an experiment to support it on the actual public internet, but it didn't sustain. But multicast is still used in some private IP networks. One example of that is AT&T Uverse, which is a cable TV and internet service. Some of you may have it as your ISP and as your TV service. They use IP multicast to deliver TV content. You can see how multicast is a really great fit probably for TV content, right? Where a bunch of people are watching the same thing at the same time. No need to send those packets individually to everybody. With multicast, you can kind of send it as a group. So basically, it's really easy to implement multicast in classic Ethernet 2. Really, broadcast and multicast are just a matter of listening to the right broadcast or multicast address in addition to your own unique address. So quick quiz here. Does Ethernet support unicast? Gotta know. Anybody else want to weigh in? So I mean, you're right in that. So okay, another interesting answer. Yes, it's just multicast with one user in the group, and that's sort of an interesting way to look at it. And so I'm going to say that the answer is yes. And it's basically like, when you put the packet on the wire, it gets to everybody, but not everybody pays attention to it, right? If you put somebody's, unique Ethernet address on it, then they're the only one that's going to pay attention to it. So I think you'll agree with me that yes, Ethernet easily supports unicast as a service model, even though the actual packet actually gets sort of broadcast. So I hope that makes sense. Let me know if you don't think that makes sense. And while you're, internalizing that, maybe also, does Ethernet support anycast? No guesses on this one? Got a yes, got a no, canceling each other out. Maybe another yes. I'm going to say no, not really, not directly, right? I mean, you could implement anycast using multicast, basically, right? But it would take some extra work to make that happen, right? Because you need to have a way to basically have everybody but one ignore it. So it doesn't natively support anycast, though you could add something on top of it pretty easily to support anycast. So yes, I think mostly no. All right, so any questions on Ethernet addresses or service types? All right, so let's move on to talking about modern Ethernet. And so far, I've sort of been hedging, talking about classic Ethernet, by which I mean like shared media with CSMA CD. But modern Ethernet rarely uses shared media. It's what we call switched Ethernet. It looks a lot more like everything else that we've done so far this semester, and notably, it's got switches in it. So in switched Ethernet, there's only two nodes on any particular link, and the nodes actually transmit on separate wires. So it's actually sort of like two unidirectional links. And so there's no possibility of collisions in these networks. And therefore, you don't actually need CSMA CD at all. And of course, there's no collisions on the switches because the switches queue packets from each link. So does everybody kind of see what's going on here? How there's sort of this evolution from classic to switched? Now, the big trick here is that switched Ethernet still mostly acts like shared media Ethernet. And what am I talking about? With classic Ethernet, the infrastructure is a single cable, right? And what falls out of that is that when you send a packet, everyone gets it, or at least everyone can get it. Whether they pay attention to it or not is a separate question. With switched Ethernet, the essential primitive, which we talked about, earlier on, is flooding. And again, what falls out of that is exactly the same thing. When you send a packet, everyone's going to get it. And so it's implemented in a different way, but it's got basically the same semantics. And so that meant the transition from like a single shared medium to a switched world was relatively straightforward. There was no big new element required here. So quick quiz here. On classic shared medium Ethernet, to support broadcast or multicast, you basically just sent the packet. So how do you do it on, how do you support broadcast or multicast on switched Ethernet? Just send the packet. So I think, yes, what's going to happen with that packet, or what needs to happen to that packet on switched Ethernet for it to actually be broadcast or multicast? I think you all probably know this. Maybe you don't know you know. Everyone needs to send it, similar to flooding. And so, yeah, the switch would need to send it to the other links. And so, yeah, like you just flood it, right? Like that's it. So, learning switches are really just an optimization here, right? Specifically, they're for unicast, right? If you know the destination's specific singular location, then you can stop flooding for that destination. But for everything else, you flood them. In modern Ethernet, some people talk about BUM Ethernet packets, which are broadcast, unknown, unicast, and multicast, BUM. And they lump them together because they're all treated the same way, by flooding, which has those same semantics as just sending on a single shared medium. So good answers, everybody. So that all making sense? All right, so yeah, I've just made this argument that like classic shared media Ethernet and modern switched Ethernet are semantically pretty much equivalent, even though they work quite differently. And I hope kind of as you think about this, you'll see sort of how the shared medium history may have sort of led to the switched Ethernet's design. Again, any questions before moving on here? All right. So now we're getting to the real crux of the matter here, which is how L2 and L3 interact with each other. So first, a quick important note. I'm mostly going to be drawing L2 networks like on the bottom, sort of for clarity, as if they were a shared media network. But like based on what we just discussed, like anywhere that I'm showing one like that, we should just be able to substitute one using L2 switches. Like that should just be fine to do. So, all right. Remember that IP is the internet protocol, and its purpose is to like compose many networks into one internet. So what are those many networks? Many of them are local networks built with Ethernet. And if it's not Ethernet, then it's some other L2 technology probably. And in the context of IP, these separate networks are often referred to as subnets. So imagine you have a couple of companies with Ethernet networks, and within their companies, their computers can easily send each other packets. They can even send IP packets among their computers, but the network, which in this case means like the cable and the network adapters on the computers, they don't actually care that they're IP packets. They just know that they're Ethernet packets. They happen to be carrying IP, but the network doesn't care about that part. But you can't send a packet between these two companies with just Ethernet. That's what IP is for. And so you add IP routers to their networks. And you connect those IP routers to other IP routers, which connect to other IP routers, and so on in the internet. And somewhere these two networks are going to meet. So if a host at Dunder Mifflin here wants to send a packet to a host at Advanced Refrigeration, it sends the packet to R1, and that's an L2 thing, right? Like the address that got it from H1 to R1 is an Ethernet address. And you can sort of see that it has to be that just by process of elimination, right? Like, because the IP destination address is going to be the same for the whole lifetime of the packet. It's always going to be some host Advanced Refrigeration. So, but the packet needs to get to R1. So it must be because we're using R1's Ethernet address. Once the packet gets to R1, R1 operates at L3 because it's a router, it's an L3 switch. It looks at the IP address and it sends the packet to the internet, where other things are also going to look at the IP address, and that's what eventually gets the packet to R2. Of course, between R1 and R2, there's also a bunch of L2 networks. So, a bunch of individual hops in there are also happening at L2, which I'm just not showing here. And remember that these networks don't need to be shared media, right? Like they could use L2 switches instead. So here I've got IP switches shown with an R for router and Ethernet switches shown with an S. And so just to finish our example, once the packet gets to R2, it's going to be an Ethernet address, which actually sort of takes the packet to its final destination. So is everybody following along here? Kind of see how L2 is responsible for some of the forwarding and L3 responsible for other parts of the forwarding? Anybody have a question or want me to walk through this again? Yeah, sure. Okay, so I'll repeat this. We'll go back. So we're going to say that H1 at Dunder Mifflin wants to send a packet to some host Advanced Refrigeration. And so it's going to create a packet with an IP address for, some host in Advanced Refrigeration. And where is it going to send that packet? You can see by looking at how this is connected that that packet needs to go to R1. And so how does R1 know that it needs to handle this packet? You need to put R1's Ethernet address on it. And so it's sort of that Ethernet address, which is going to take the packet from H1 to R1. Like that's what's going to be responsible. If you put H2's Ethernet address on the packet, then it wouldn't get to Advanced Refrigeration, right? So part of the forwarding is kind of taking place at L2. In this case, it's pretty trivial because it's a single shared media, but it could be a switched Ethernet, right? Once it gets to R1, R1 is going to look at the IP address of the destination IP. And it's going to say, oh, well, this is somewhere else on the internet. And so it's going to send it, into the internet. And eventually the internet should get it to R2. And once R2 gets this packet, it's going to say, well, somehow I know this packet needs to go to some host here in Advanced Refrigeration, like we'll say H2. And so I'm going to need to put, H2's Ethernet address on it and put it into the network. And so, here I've shown that, it's going to put H2's address on it, and that's somehow going to take it to H2. Does the packet contain destination L2 addresses? Yeah, so it does. We looked at this way earlier on. I don't remember which lecture, but the packet's generally going to have this stack of headers, right? And so it's going to have an L2 address. And then it's going to have an L3 address. And the L2 address is going to change a bunch of times. Like, the L2 address when this packet is in Dunder Mifflin is going to be one thing. When the packet gets to Vance Refrigeration, it's going to be a different set of L2 addresses because those are local to those networks. On the other hand, the L3 addresses are going to be the same across all of it. So I hope this makes sense. I hope that clarified a little bit. Let's actually walk through the next couple examples, and you can tell me whether those, help you make even more sense out of this. First, a couple notes here. And the first is that there's no reason that you can't use IP routers to connect local networks together in a private part of the network too, like that is without going through the internet. So like here, maybe this is a university network and it's got separate Ethernets for computer science and EE and biology. And again, you'd probably call these subnets. And they're connected by IP routers. And there's also no reason that your Ethernet needs to have more than 2 nodes. Like in this case, we've got 2 Ethernets, which only have 2 nodes. Like the router is one of the nodes for both of them. And so this isn't like a single Ethernet because they're connected by a layer 3 switch or a router here. So there are 2 separate Ethernets. If they were connected by an L2 switch, then basically we'd consider them the same Ethernet. So let's do these kind of more detailed examples here. So we've got this network here. It's got 2 Ethernet subnets connected by a router. And you can see that the IP addresses have been allocated in such a way that all of the addresses on a subnet have a common prefix. And I've shown R1's table here. And these 2 entries in this case would be static routes when the network designer decided that the network on top would be 10.0.0.0/16 and the bottom would be 10.1.0.0.6/16. He or she would have plugged the static routes into the router. And like note that because they all share like a common prefix, like you could add like 65,000 hosts onto either one of these subnets without changing those routes because we're using, the entire prefix in the routing table. And note that the router ports have different addresses. Each port has an address in the appropriate range for the subnet that it's on. A side note here is that I've made the Ethernet addresses pretty simple, just for clarity, maybe too simple. In the real world, they could and would be like pretty arbitrary. They wouldn't match the IP addresses or host names in any way. So I hope you all kind of see what we're looking at here. And so let's do an example where H1 is sending an IP packet to H2 on this network. And they're on the same subnet. So this should actually be really easy. Like if H1 just puts the packet to 10.0.0.2 on the wire, it should get to H2. So is that it, or are we missing something? Anybody think we're good now? Anybody think we're missing something? So do you need R1's Ethernet? And so in this case, you don't need R1's Ethernet address, but you're on the right track. What you need, since we're sending this packet to H2, we need H2's Ethernet address, right? Like without the right Ethernet address, the host is just going to ignore it. So somehow, we need to find out H2's address. And so, one option you might think would be, well, okay, what if we just put the broadcast Ethernet address on there, right? Like that should kind of get it there. H2 should be listening to the broadcast address. A couple downsides here are, first of all, like this doesn't allow for, taking a learned path, which doesn't apply to this network since there are no switches, but, in general. It also kind of annoys, I wrote annoys other nodes on the network here, and I actually mean something really specific there. Like usually network interfaces themselves like filter out packets to addresses that they don't care about. So even if there are many packets on the wire, like if they're to different addresses, the CPU and the OS never need to know. But when there's a packet to an address it cares about, the CPU and the OS have to actually process it. So if the CPU is in a low power state, it's got to wake up, and the OS needs to serve an interrupt and actually run the packet through its networking code and so on. There was a day when that processing was like expensive enough in terms of CPU usage that it could actually slow machines down. I think on machines today, that's probably rare. I think the bigger issue is probably power consumption, like battery life. It has to wake the CPU up for every packet. Even that's probably not a huge deal, but it's certainly like bad form and kind of needlessly wasteful. This also doesn't necessarily work. Like a lot of OSs will actually ignore unicast IP packets sent to the broadcast Ethernet address. So what we really need, like I think you were kind of getting at there, is we need the correct Ethernet address, which in this case is H2's Ethernet address. And so the question here is, how do we find that? How do we know that? We know the IP address. How do we get the Ethernet address? And the answer is a protocol called ARP. And so ARP is the address resolution protocol, and it solves this specific problem. Like given an IP address, you want to know the corresponding Ethernet address. ARP runs directly on top of L2. It's not, on top of IP. And ARP makes use of L2 broadcast. And so basically a host just broadcasts a message asking who has this particular IP address. And the host that has that address answers the query and just unicasts back an answer that tells it the Ethernet address that it has. Hosts cache the results of this in what's called an ARP table or a neighbor table, and then occasionally resend requests to make sure that the table is up to date. So that's all the ARP you need to know for this class. That's really most of ARP. And so pretty simple. You just call out asking who has this IP address. Whoever has it tells you their Ethernet address. So back to our example, we use ARP to find the Ethernet address that corresponds to the IP address of the destination. But we actually skipped over another important question here, which is, how did we know that H2 was on the same subnet? And keep in mind that ARP relies on a local broadcast, right? Like if H2 was on the other subnet, then the ARP wouldn't have gotten there and you would have never gotten an answer. So how did we know that H2 was on the same subnet? We already sort of grazed this in a slightly different context during our discussion of CIDR. Does anybody remember the sort of relevant technique that we can use? Yeah, you check the prefix. We showed that, using a net mask or using a prefix. In this context, it's usually called a subnet mask. And so, basically by just sort of like logically, or rather bitwise anding the mask versus the destination address and the mask against your address, you can see whether you're on the same network or not. This, of course, raises the important question of how a host knows its own network mask, which I'll come back to in just a second. But before I get to that, any questions on this? I'm going to move on to another example if there are no questions on how this one works. That you first check, you find out the H2 is on the same network, then you can ARP for the Ethernet address, and then you just put the packet on the wire with the right Ethernet address. Let me know if that's not clear, and I'm going to move on to the next example. So for this example, we've got H1 sending to H3. And this time the hosts are not on the same subnet. And that means that we must be sending the packet through a router, right? That's what it means, that when we're on a different subnet, it's got to be somewhere else. So we need a router. So we're going to assume that the host knows the router's IP address. Again, we'll come back to how it knows this in a minute. But let's look at the packet headers when H1 sends the packet. So the source IP and the source Ethernet address are pretty obvious. They're just going to be H1's addresses, right? The destination Ethernet address, Evan, what's it going to be? The destination Ethernet address is going to be R1's Ethernet address, right? It's this destination IP is going to be H3's IP. The destination Ethernet address is going to be R1's Ethernet address, right? So yes, you're right. It's going to be R1's Ethernet address because this time it does need to cross this router. And so when R1 gets the packet, it's going to have to forward it itself onto, this other subnet. And so, first of all, how did we know that this was the Ethernet address that we wanted to use here? We knew the router's IP address. How did we know the router's Ethernet address? Right, we ARPed for it. Perfect. All right, so the packet headers, once R1, it's now R1's job to forward this packet. I thought the ARP was only local. Yeah, so though if you look at this, I mean, R1 is actually local to both subnets, right? It's got an interface on both of them. And so when you're ARPing for R1, your H1 is sending out an ARP for 10.0.0.254, the router's IP address. And so R1 can answer it. It is local to H1. It's also local to H3 and H4. So yeah, good question. So it's not R1 that does the ARPing here, like for H1. When H1 wants to send the packet, and it knows that it needs to send it to a router, it knows it needs to send it to R1. So how does it know the Ethernet address for R1? And it does that by ARPing for R1. Yeah, how would we know the router's the IP address? I'm going to come back to that in just a minute. Good question. Okay, so now we've got the packet at R1. And so what are the source and destination IP addresses going to be here? For this packet going from H1 to H3. Yeah, you've all got it. They're going to be the same, right? Like these don't change. What about the source Ethernet address? What's it going to be when R1 forwards the packet? So it's going to be R1's, yeah, router's Ethernet, right? It's going to be R1's Ethernet address, specifically R1's Ethernet address on the Ethernet that it's forwarding the packet to. And the destination Ethernet address is going to be what? Right, it's going to be H3's Ethernet address. And how did R1 know H3's Ethernet address? It ARPed for it. Perfect. All right, so just to jot down some of the things that we noticed that we needed a host to know. It obviously needs to know its own IP address. It needs to know its subnet mask, or the size of the prefix of the network that it's attached to. And with those two things together, you can find out, like if something should be directly reachable at L2 or whether you need to go through a router to reach it. So why does the source IP, we've got a question, why does the source IP not change at the router when R1 sends it? So the source IP doesn't change because the packet is still from H1. At the IP, at the IP layer, it's still from H1. So the IPs are never going to change. Well, actually, there's a caveat to that. But in general, the IPs shouldn't change, right? The packet still came from H1 at the sort of global L3 level. At the local level, it's changing who it's coming and going to. But at the global level, it's the same. You can sort of think about this like when the packet gets to H3, if H3 wants to send a packet back, it needs to know H1's address. So it doesn't change there. Right. So we also need to know the IP address of the router. We had the question about how we know that. We didn't use that directly. We used it to get the Ethernet address. But I said, what we're going to get is the IP address of the router. We can ARP to find the Ethernet address. And so let's talk about how we learned those things. Does ARP form a table so redundant queries are not asked? Yeah, it's basically exactly that. It's like a cache, right? It's like, you know, if you keep communicating with R1, you don't want to have to send an ARP for R1 for every single packet. So you keep this table, and just every once in a while, you look up R1's Ethernet address, and then you keep it in a table and just check it again every once in a while. So yeah, good question. Okay, so how do we know those things that we said we needed to know? And so the single most important thing that we need to know really is our own IP address. And if we think about Ethernet addresses, like the sort of ground truth, the thing that dictates Ethernet addresses is basically the hosts themselves, right? Like I said, it's like burned into a chip on the network adapter. And so it's therefore clear that like the state in the network, the routing state, the state in switches needs to adapt to the hosts in this case. And so that sort of motivates the learning approach. On the other hand, the ground source, the ground truth for IP addresses, you know, you can't just pick them out of a hat. Like something else dictates them. And there's a couple answers for this. Like you could say static routes on the routers dictate what those are. So those are something that, you know, the network designer operator puts in. You could also think about it as they're dictated by the allocation of addresses that you got from like Aaron, right? For your AS, you've got some set of addresses. And of course, those inform the static routes that the operator includes. And so, you know, really it ends up being sort of exactly the opposite, right? Like the authority doesn't come from the hosts, it comes from the network or one of the regional registries or ultimately from IANA. And so you end up with this opposite where like the hosts need to adapt to the network in this case. And so you could think about ways to do that. And one would be manually. You could actually like, you know, plug in static addresses on the hosts the same way you plug in static entries on a router. That would have worked pretty well at one point in time. It did for many years. These days, you know, with laptops and other mobile devices, when we're not all trapped at home, that would be a real pain to change your network configuration manually all the time. And so we end up with this protocol called DHCP. And it sort of is built on this idea that, you know, the network has already been configured with the correct information. And so we just need a way to sort of query the information that the operators are already putting in the network. And so DHCP is the dynamic host configuration protocol. And basically it lets hosts find out the stuff they need to know. And crucially, this includes the IP address that the host should use and its netmask, and what's often called its default gateway. I've mentioned before, gateway is like a sort of antiquated term for router. So really what this is talking about is the first hop router. And so that is the answer to all those questions. This also often includes like the local DNS resolving server that you should use on that network. And there's like a bunch of other stuff as well, which I'm not going to talk about at all. So the way this works, kind of digging into it pretty quickly here, is that you start by adding one or more DHCP servers to the network. Usually it's just one, but it doesn't have to be. And these servers can be a separate machine or they can be built into a router. Like if you have a normal home Wi-Fi router, it's got a DHCP server built into it. The servers listen on UDP port 67, and they're configured with all the required information, like the first hop router address and the local DNS server. In the case of your local home router, like the router is probably both of those things. And the DHCP server is also configured with a pool of addresses. So like some number of usable IP addresses. And basically the server gives clients a lease for one of those IP addresses. And the lease is valid for some limited time, like hours or maybe a day. If the host wants to keep it, it has to renew it. Otherwise it gets returned to the pool. But as long as a host has it, the server is not going to lease it out to someone else. And so there's a number of different DHCP message types, but we're going to discuss the 4 really important ones. And so things start out when a host joins a network or powers up or whatever, and it sends a DHCP discover message, which is basically just asking for configuration info. And the DHCP server is going to send an offer with an offer for a lease and other information. The client is going to select the offer that it wants. It may have gotten more than one, so it's going to select the one that it wants, and it's going to send a request message saying that it wants it. And then the server is going to send back an acknowledge message, which confirms that the request was granted. So we've got a couple questions that come up here. And so the first is like, how does a client know the server's IP address to send these queries to? Anybody quickly have a suggestion on how they think you might do that? So it's a tough question, right? It might not know the address. We've got the question of what if there are no IP addresses left in the pool? In that case, you don't get an address. It's as simple as that. So it's definitely possible that a pool gets exhausted and then you can't get on the internet. So we got one suggestion, maybe this server continually sends out an IP. Good suggestion, not actually how it works. How it actually works is that you broadcast messages to the server instead. And so this also works if you have multiple DHCP servers. This gets to all of them. We've got this question, so the offer still gets sent through. And so that's actually a good question. If there's nothing in the pool, I think most DHCP servers will probably just never send the offer. But I don't actually know that for a fact. Yeah, I wrote a DHCP server and it just doesn't send one, but I'm not sure if that's true for all DHCP servers. Okay, so turns out, the same way we can use an Ethernet address of all ones, if you use an IP address of all ones, then that'll do like a local broadcast. Again, there's no such thing as like an internet-wide broadcast, but if you send an IP packet with all ones as the destination address, then it'll get turned into an Ethernet broadcast. And you've also got this question of like, what IP does the server use to send a message back to the client? Because again, the client doesn't actually have an address yet, right? That's part of why it's doing DHCP. And so again, it broadcasts messages. And then you've got this question of like, what's the source IP in the packet header in the packets from the client? It turns out they usually just fill it in with zeros. And so anyway, you can sort of see that like typically these are all broadcasts, at least initially. During a renew, they may have actual unicast addresses in there, but usually this is all broadcasts, which also has the nice benefit of if there are multiple DHCP servers, when the client sends a request, the other DHCP servers can see that their offer wasn't the one that was accepted. So a quick quiz for time management, I'm going to answer this. But what does broadcasting imply about the location of the DHCP server? Or someone else, quick, jump in if you know the answer off the top of your head. I want to make sure we get to the end of this though. It must be local. Yep, perfect. You guys know this. So if it's not local, you can actually have something called a DHCP relay, which is, usually it's a router feature that knows how to forward DHCP across different networks. So that's a thing that exists. So I'm gonna skip this again for time management. And so now we have all the pieces to do an example, which brings a lot of stuff together. I do really want to kind of quickly review some of the stuff that we've talked about today. So first, hosts know their Ethernet address because it's burnt right into the hardware, right? They know their IP address because DHCP told them. They learn how to map between an IP address on the local network and its Ethernet address using ARP. And DHCP also lets you learn your subnet mask and the first hop router IP address and the local DNS server. And finally, both DHCP and ARP use a lot of broadcast, right? And the scale's okay because it's only broadcasting to the local L2 network. And, it's like using this broadcast address lets you kind of solve these chicken and egg problems where you don't really know what address you should be using. So you just kind of address packets to everyone. And so here's the setup for this kind of final example. We've got this network with two subnets, kind of like before. They're connected by a router, R1. And H1 is going to be our client machine, and it's just booted up. So it doesn't have any state. Its ARP and DNS caches are all empty. It doesn't have an IP address and so on. And what it's going to do is it's going to fetch one file from a local web server, H2, It goes by the DNS name h2.com. And then it's going to fetch two small files from a web server called h5.com. And so our task here is to actually list all of the packets that h1 sends and receives. A few assumptions here. We're going to use persistent HTTP connections. We're going to say that the browser times these out when they've been idle for a minute. And second, we're going to assume that all the HTTP requests and responses fit in a single packet, so very small web pages. And third, we're going to say that there's no TCP piggybacking. And what that's saying is, there's like every TCP packet contains an ACK number. So like a packet sent as an ACK could also theoretically have data in it, but that doesn't happen in this example. Really quickly, why that's true, why that's realistic, is TCP is typically implemented in the OS kernel, right? So the ACKs are generated in the kernel. On the other hand, applications like HTTP are typically implemented in user space, right? It's just a normal application. And so their requests are processed and replies are generated in user space. And so the ACKs often get generated before an application has a chance to respond. Like the kernel gets a packet and immediately sends an ACK. And it schedules the application to run, but the application's not actually going to run until sometime later. So there are a couple exceptions here, like if you're doing something called delayed ACKs, which we haven't talked about. And it's also not true if the kernel actually has data already waiting to be sent, but that doesn't happen in this example. Something similar happens with TCP closes. It's why you usually see a fin, an ACK, and a fin and an ACK, 4 packets, instead of 3, a fin and then a fin and an ACK for that fin and then an ACK. And so in what follows, no piggybacking, except for the SYN ACK, you might say looks like a piggyback, but the SYN ACK, when you're opening a connection, is done entirely in the kernel. Does this all basically make sense? All right. So at the high level, I said what we're going to be doing here is have H1 boot up and then download some files. So let's make a detailed to-do list here. So I'll start us off. The very first thing that's going to happen is that H1 is going to use DHCP to get configured, right? And now we're going to want to download this small file from h5.com. What is the first thing we need to do here? Yeah, we're going to need to do DNS. But before we can do DNS, we need to do something else. In order to do DNS, we're going to have to ARP to get the not the IP, right? To get the Ethernet address of the DNS server, right? So we're going to ARP for the DNS server. Then we're going to do the DNS. Then we're going to actually be able to to download this first file, which is across the network. So we're going to need to ARP for R1's Ethernet address. Once we know that, we can open this TCP connection for H5. Then what comes next? We've opened a TCP connection to the web server. So we can do an HTTP request. The purple, I'm just kind of separating the steps. First we DHCP, then we're going to do this resolution. Then we're going to do in blue again. It's just all this, all the stuff related to kind of fetching the file from the server. Once we get this, it's going to time out. We're going to close the connection. Then we're going to resolve H2. Then we're going to, now notice when we resolve H2 again, we don't need to ARP again, right? Because it's going to be cached at this point. Then we can ARP for H2, open the connection to H2. We can do HTTP request for H2, do the second HTTP request for H2, right? There's 2 files. And then eventually we're going to close the connection here. So, all right, we're pretty much out of time right before we get to where the rubber really hits the road here, unfortunately. I will keep going. You will probably want to look at this. Yeah, okay. I'm gonna go along so that we have it on the recording so that you can watch it. Perfect. All right. So here's what we'll do, and you can watch this after the fact if you have to go now. So now we're gonna look at this at the packet level, at packet level detail. And so looking at our to-do list on the right, the first thing we're doing is DHCP. And so if you remember DHCP, that starts out with this discover message. And so basically, I've shown this dir column showing the direction. And so arrows pointing to the right are messages that H1 is sending. If it's pointing to the left, it's going to be a message that H1 is receiving. And I put a double arrow as a way of showing that it's a broadcast. The O here is the other host that's involved. In this case, it's a broadcast. There's no specific host. And then the next column is the transport protocol, which is UDP for DHCP. And then this is a DHCP discover message. So hopefully that all basically makes sense. If it doesn't and you're still here, feel free to chime in. So the next thing that happens, the next part of a DHCP transaction is going to be an offer. So the server, which in this case is the DHCP server H4, is going to broadcast back an offer. Following this, the host H1 is going to send a DHCP request. It's going to basically saying, yes, I want that offer. And then the server is going to broadcast back a DHCP acknowledge. So that finishes up our DHCP part. And we can move on to this next part where we're trying to resolve h5.com. But before doing that, we need to find out the Ethernet address of the DNS server. And we do that because it's a local DNS server. It's on the same subnet. So we send out an ARP request for H3. And that's a broadcast. H3 is going to send back an ARP response to H1. And this is a unicast. It's not going to be a broadcast. It knows who was asking. It can send back a unicast right to H1. So that finishes our ARP. And now we can send a UDP packet with a DNS request for an A record for h5.com. The DNS server is going to send back the response. And so now we've resolved h5.com. We know the IP address to use. We can look at that IP address for H5 and we can see that it's not local and therefore that we need to go through the router. So we're going to ARP for R1's Ethernet address. And we know R1's IP address because we got it from DHCP. So again, we get a unicast back from R1. Yeah, the difference between single arrow is a unicast and multi-arrow is going to be a broadcast. Sorry if I didn't make that clear earlier. Now we've ARPed for R1, and now we can create a TCP connection to H5. So we send the SYN packet, and what happens next? Somebody who's listening want to chime in? What's the next packet going to be? Right, it's going to be a SYNAC coming from H5, right? It's going to be unicast from H5, transport protocols, TCP. Then, of course, the third part of the three-way handshake is going to be the ACK. And then what happens after this? Multi-arrow is broadcast. Yes, you're right, it is. So HTTP, right. So we're going to get this HTTP over the TCP connection to H5. What's the next packet going to be? This one's a little bit tricky. Yeah, but you got it. It's going to be the ACK from the server. It's just ACKing the fact that you got this HTTP GET. Then it's going to send back the actual HTTP response. So what's the next packet going to be? Right. You got it. It's going to be an ACK from the client saying, I got the response. And then nothing's going to happen for like a minute. Right? I said there was going to be this delay between the downloads. And so the next thing that happens is after a minute, the browser says, okay, this connection's idle, and it's going to send a fin. And I'm sure you all can guess that the server is then going to ACK that fin, send its own fin, and the client is going to ACK that fin. So with that, we've now disconnected from H5. That all makes sense so far? All right, so the next part, there's nothing too interesting, too new here. We've got to resolve h2.com. We can just do that. We've already cached, the Ethernet address in our ARP table for the DNS server. So we can just send that DNS request for the A record for H2. We'll get back the response. Then what's the next thing that happens? We need to ARP for H2. We're going to get the response back. Again, the ARP request is broadcast. The ARP response is going to be unicast. You can think about that. The request, you don't know who is going to answer that, so you need to broadcast it. On the other hand, the one answering it definitely knows who asked the question, so no need to broadcast that. So that gives us H2's Ethernet address. We can then do the three-way handshake to open the TCP connection to H2. Then we do this HTTP request to H2. We get the ACK, get the response. We ACK the response. This is pretty much just the same as before. So that gets us our first of the two files that we said we wanted to download from H2. Then, since this is a persistent connection on this same TCP connection, we can then send the second HTTP GET. It'll get ACKed. We'll get the response. We'll ACK the response. And that's gotten us our second file. And then again, after waiting for a minute for the browser to decide the connection is idle, the browser will send a fin, and we'll do the 4-step TCP connection teardown. And that finishes this up. Any questions on this sequence of events? All right, so that's like from start to finish how a host would download some web pages, like packet by packet. And so that's something I don't think you would have been able to do when you started this course, but hopefully with a little bit of practice, now you will be able to. It's a good thing to know probably for the final. And so that's everything for today. Sorry I went a bit long. This was my last lecture. It'll be Sylvia from here on out. I'll still be around on Piazza and email, of course, and I'll have office hours on Thursday. So thank you all who stuck around. Sorry for those of you that are watching this after the fact. I wish you all the best on the project and on the final exam and on the rest of your courses this semester. Again, thank you all very much.